So I kind of changed the title of my talk at the last minute, but yeah, so I'll be talking about deep level diversity in multi-robot controllers and how we can actually get that. So, we all know that multi-robot systems, we're having a hard time getting them out of the lab and into the real world. And the question is why? So there's been lots of success in manufacturing, in warehousing, and in the military, but the areas that we're really interested in, like automated delivery, emergency response, self-driving vehicles, and even modular robot surgery, there are some issues that are holding us back from actually getting multi-robot systems out into the real world. And part of the reason why some of these things have been successful and some of them haven't is because in manufacturing and warehousing, the interactions between the robots and between the robots and humans are highly engineered. The robots are often hand-trained. They have limited capabilities. And they operate in very structured environments. So this is not, none of these are very structured environments below. And in the military, the robots are also teleoperated. But in these environments, we have very unstructured, very dynamic environments. Things are changing rapidly. We don't have infrastructure that's already there. They require autonomy because you want to be able to take your system and apply it to different things. If you have robots that are delivering packages in one area, you don't want to have to come up with something totally different, and you don't want to have to hand tune anything just so they can deliver something in a different area. The robots are usually multifunctional, so a quadriga can be used for delivery, it can be used for emergency response, it can be used for a lot of different things. And on top of that, the goals and the risks that we have in these environments are a priori unknown because we don't have the structure in the environment. The environment is not static, everything is changing. And so every time we deploy our team of robots, they have a different set of goals. They don't have time to optimize for every single task that we have to do. So let's talk about a simple example. Let's say that I want to deploy a team of robots to this nuclear power plant. There's been some kind of disaster. And so if I take the traditional approach that we take, I'm going to find the shortest path to get there, or the least cost path to get there, and I'm going to hope that I can travel along this path. So I have some information, though, that tells me that this path is not the best because part of it is blocked. So what I'll do next is now I'll try to think about, okay, what are the other ways that I can actually get there? So there's several other ways. Let's choose these two. Now I have to decide between these two. Well, I might try to calculate the risk of going in either direction. I might then choose that, okay, let's actually go in this direction. So I started the robots driving in that direction, and I'm assuming everything's free and clear. I've evaluated my risks. I have created my heuristic function. I've used that to decide which way to go. But then I found out, oops, this part is also blocked. So now I have to think again and resolve this problem. So the way that we actually solve our robotics problems are we have this problem, we formulate it, we decide what are the things that we're willing to deal with, we analyze the problem to death often, and we try to come up with a solution. So we do this in a very linear way. But there's often many solutions to the problem, and we know this, right? There's many multi-robot controllers that'll take my team of robots from point A to point B. It just depends, the best one depends on what the environment looks like. It depends on what the risks are. And so if we don't know the risks, how do we actually choose the best way? I'm not sure there's actually a way, if we don't know the risks, to choose the best way. So why not choose all the ways? So diversity has been studied a lot in I guess sociology or psychology, and it's been shown over and over again that diverse groups actually outperform homogeneous groups. So the little asterisk is actually because there have been studies that have shown that when we have diversity, we actually introduce more conflict into the system. And so people leave kind of disgruntled, unhappy, but the studies also show that conflict creates better solutions. So while having diversity can create conflict, and so here I'm actually showing what's called surface level diversity. So diversity that you can actually tell the difference if you're actually looking at something. But what I really want to talk about is deep level diversity. So deep level diversity includes, for example, informational diversity, diversity that comes from kind of knowledge that you have, value diversity, which comes from what you actually value. And so combining solutions from these different types of people or different types of robots can actually lead to better solutions. So sure you recognize this image from Spring's talk. Thank you, Spring. So ants actually do this, right? So, obviously not every different kind of ant, as Spring informed me of. But there's plenty of types of ants that can take on different roles in the task. And so I know this is an example of pushing objects, or pushing and pulling actually, but ants can change from being foragers to recruiters, to doing tandem runs, to doing all these kinds of things, and they're all, hopefully, Spring will correct me if I'm wrong, the same kind of ant physically. It's just that they take on different roles based on the environment. And so when we're actually coming up with multi-robot controllers, why don't we do this? Why don't we just have kind of, maybe some randomness dictate what different robots do? Why don't we have different controllers for robots to do the same task, but in different ways, so that we can be robust to all different kinds of environments? So humans have been studied in robotics, but not that extensively. So, for example, one of the works that has been studied is by Ross Knepper and Daniel Roos, and they studied the way that, well, first they studied how humans can be helped by robots, but they've also studied how humans walk past each other at intersections and how they kind of signal to each other that they're going to go in a certain direction, how we actually avoid collisions while we're walking on the sidewalk. But there really hasn't been much more than that as far as studying humans for robotics. And part of the reason is that humans are really complex. So, everybody should recognize this man, obviously. But he's communicating with you. Just because he's not talking to you, you're still getting a message from this image, and it's not moving. It's not explicitly communicating with you. So humans are super expressive. We have different kinds of communication modalities that, our robots, not so much. As much as we try, our robots can't be as expressive as the human face. So there's many reasons why. So first of all, of course, we have a lot of different modes of implicit communication. We can point, we can make faces. There's also different ways that we can communicate explicitly that are hard for robots to do in large groups. So communicating one-to-one for robots in a large group is difficult because you need to know the address of the other robot you're talking to, and in order to share relevant information, you need to know where that other robot is relative to you. Broadcasting is also difficult because if you want to broadcast useful information, you have to know where it comes from. Nobody cares where a robot was standing when he's going to be talked, right? On top of that, we have more complex sensors that our robots have. We can hear, we can see, and all this is being processed by our amazing brains. And so robots have constraints on communication, on sensing, on motion, and processing that we don't have. And so it's really hard to learn from groups of humans how to coordinate teams of robots. And so what we decided to do is, instead of solving the problem of can robots act like humans, we decided to solve the problem of can humans coordinate under robot-like conditions. So if we give humans the conditions that robots have, with their limited sensing and processing, communication, can they actually get humans to solve complex tasks? So we do this by developing an online game. So we developed an online game where if you're playing the game, this is you have the Senate here. And so this is your local view. You kind of see what you would see if you were a robot with a laser rangefinder. So you see that there's some other agents that are around you, but you don't know there could be another agent over here or another agent over here. And then we also get a global view. So in this global view, you can see the pattern of what everyone else on the playing field is doing. And so we actually played this game several times, and we tried different things. So here we have people are playing the game now with both a local view and a global view. And we asked them to form an empty rectangle of a uniform color. So this is what ends up happening. So here you see this agent 6 was moving in a distinct pattern, and basically what it's doing is it's trying to localize. So people came up with different methods of localizing using just the limited information that we gave them. So they can move up, down, left, right. They can change their color. And here, number 2 is actually signaling to these other agents that they're in the wrong spot and they need to move. So a rectangle is too small. It's not going to fit everybody. And so basically we took away language, but they brought it back. So they brought it back by using implicit communication. And you can see this guy's also kind of localizing last minute. Being a different color than everybody else makes it easy to know who you are in the global view. And so I guess I forgot to tell you that in the global view, that they don't actually know where they are, right? You have to figure it out. So looking at kind of the environment that's around you and looking at what's going on in the global view, you kind of have to figure out and match together where you are in that world. Otherwise, you're not going to be able to figure out where you are relative to everybody else, and you're not going to be able to contribute to the task. So we also wanted to see what would happen if we started taking away information. So how low can we go? And so what we did was, next we took away the local view. So we said, okay, you no longer see what's going on locally around you, so it's like removing the laser rangefinder. All you get is this feedback from the global, like an overhead camera. And so we asked them to form a circle of a solid color. Actually, we didn't allow them to change colors here. So a circle is very different than a rectangle because it doesn't have corners, so it's harder to see where the shape starts forming, but you can, of course, tell that something is definitely going on here. And so, people slowly end up kind of figuring out where they are, and we realize that the global view actually is a lot more informative than the local view. And of course, this is a little bit of a contrived example because we have, a scenario that you might not necessarily have in a robotics problem that, in the real world that we're trying to solve, but you have to start somewhere. And then we thought, okay, so the global view is so important. What if we get rid of the global view and we only have the local view? And this was something that we didn't know if it was actually going to work. Because if you only give people the local view, then how do they know where to go to find the rest of the group? If you're in the middle of nowhere, you have to do like a random walk to try to find the rest of the group. So here we go. So what you'll end up seeing is that different formations start forming in different parts of the environment. And so you can see that there's like multiple different rectangles that are starting to form. And if each of these groups ended up being equally stubborn, and they kind of stuck to their guns and said, I'm going to stay here, and this is where the rectangle is going to form, then this actually would not have been solved, right? Because you'd end up with like 2 groups or 3 groups of rectangles, and nobody would find anybody else because they'd just be stuck in their ways. So having this little bit of diversity and maybe a little bit of randomness, because people might have been kind of second-guessing themselves, you actually get this solved. And so what happens is at the end, they have an idea of how many people have been playing the game, so they know how big the rectangle has to be. So they end up finding that this is where the rectangle is forming, but in the end, because they have no global feedback, what happens is they basically form the rectangle, but nobody really trusts that it's there, and so they end up kind of leading the group and walking around and making sure that it's a rectangle and going back, and by the time one person goes back, another person's already starting to do that. But you can see that they're fairly successful, even though they only had this global view, but they knew how many people were playing the game in general. So some of the things that we're trying to learn here is, what are the transferable skills that we can learn from this? So one thing that we can learn is localization. So here, this agent is localizing by traveling in a very distinct pattern and changing their color. So they're kind of cross-referencing what's going on in the local environment with the global environment, so that they can figure out where they are in the world. So here, this agent number 15, and agent 15 does this almost consistently throughout all the games that we played with them. We played about 7 or 8 of them with one group. So agent 15 here is almost always a different color than everybody else to the last minute. So I call this lazy localization, but it means that it's really easy to find out where you are in the global environment if you're the only blue one on the screen. And of course, we can also learn signaling. So here, agent 2 is, and agent 2 does this consistently also, is constantly bossing other people around, telling them that you're in the wrong spot, it's time to move. And here in this video, it also does the same thing. So here we had an agent that was introduced by a bug that we had in the system. And so 26 was not a controlled agent, it was just kind of sitting there, not moving. And so what happens is, everybody's walking in a circle already, but this guy's still here, so they can't finish. And so agent 2 leaves and kind of tries to boss this guy into coming back and joining the group. But the guy's not having it because there's no one there. So we've already learned, different methods of localization and signaling that we can actually transfer to real robotics problems. Another question we're trying to answer is is how much diversity is necessary. So this comes back to the kind of composition. How do we actually compose a team that will actually work? And so how many of these leader types do we need? How many of these follower types do we need? And what are the types that actually exist? So we're analyzing the data and trying to figure out, what are the different, we'll call them personalities of the players in the game. And, how do we actually mix them so that we can come up with successful teams? Are traits inherent? So this is more of a people question than a robotics question, but it might help us answer some robotics questions as well. Are people consistently playing the same way? So we know that some of the agents are consistently playing the same way, but we haven't gotten down to the level of detail where we know that everyone's kind of playing the same way. So sometimes some people are leaders, sometimes they're followers, and we're not really sure how what factors change that. Is it location? Is it local density? And another question we're trying to answer is how is consensus reached? Somebody mentioned this yesterday. How do we actually know when the task is complete? So none of the shapes that they formed were perfect rectangles or perfect circles, and yet everybody was satisfied. How do we actually automate that? How do we know when we're actually done? This is a really difficult question, and we all kind of take it for granted that we know that we're done, but it's really a difficult question. And I just wanted to quickly show you the test bed that we're planning on using this on. So this is a very recent experiment that we did in collaboration with Gaura's group. So we have we're calling Crazy Swarm, 49 Crazy Fly quad rotors in a new warehouse space that we have. So this is something that we just submitted to IROS late-breaking reports. So hopefully it'll be shown there as well. This is actually super challenging to fly 49 UAVs indoors. It's a really big communication issue. Trying to get all of them controlled, all of them doing onboard state estimation when they're so small and have really junky processors. I should have maybe sped it up a little bit, but I have time. Also, when you're flying them in such close proximity, you have to figure out by trial and error, I guess, that you can't have them all take off at once, and you can't have them all land at once, or you end up with some very beautiful catastrophic videos. So hopefully we get to use this as our test bed for that project, although we might start with ground robots. So a little USC plug here. Okay, so in summary, we know that obviously today's robots are not capable of coordinating like humans because they have a lot of limitations. They don't have the sensors, they don't have the communication capabilities. But there's still a lot that we can learn from human coordination, and that's what we're trying to do with this project. On top of that, diversity makes teams work better. And even though there are some conflicting studies on that, the truth is that and studies have shown that that conflict within a group makes outcomes better. And so I hope that we can all start thinking about diversity that's beyond physical heterogeneity. Diversity that's in the way that robots solve problems. If everybody's solving the problem the same way, then we end up with problems. We end up with maybe local minima. We end up failing in certain kinds of environments. And so if we think about how robots can solve problems in complementary ways, but at the same time different ways, then I think that we can come up with some really interesting solutions. So this work was funded by NSF, and I'm actually looking for a postdoc. So if anybody has somebody who's graduating or graduating soon, let me know. And one final plug is that I'm actually one of the co-chairs of the TCM Multi-Robot Systems, and we are starting a new Multi-Robot Systems conference that'll alternate years with DARTS. The first one is going to be in December 2017 at USC. It's meant to be inclusive of all different things that are relevant to multi-robot systems, which is a very broad field, encompasses sensor networks, and all different kinds of things. So anything that's related to multi-robot systems is welcome. Please submit your high-quality papers. We're trying to start small so that we can start very high quality and maintain a high quality throughout. All right, thank you.